yourself.
Yes, thank you. Thank you very much for being here.
Of course.
So I'd like to introduce everybody to Dr. Mathias Appel from Shell Global. Mathias, thank you very much for being with us today, sharing a little bit of your knowledge. We are here with several members of EROP, and there are other members online as well. So thank you once more, and the floor is all yours. If you want to share your screen, please go ahead. Thank you so much.
Very much so. Let me start off by saying it's really an honor to be have been invited to your seminar, and I hope you can understand me well, and I hope you can understand my accent. If you can't understand it, just let me know, right? Give a sign, and I will probably repeat the same sentence with the same accent again, right? Let me see whether I can share my screen. You should see a PowerPoint presentation called Improved Core Analysis through Multiscale Imaging. Can you confirm that you can see it? I take that as a yes, right? So basically, what I would like to show you is what we are doing in Shell on using multiscale imaging to improve our core analysis workflows, to reduce the uncertainties in our measurements, and to basically sometimes even replace measurements which would lead to erroneous results if we followed our standard workflows. I was told that the presentation should take about between half an hour and 40 minutes. So roughly in the time scale, what I had in mind was to tell you about something like what we do with core analysis and how imaging plays a role in the core analysis workflows, how multiscale imaging comes into the discussion, and not only for the geoscience kind of applications, but also for other industries. And then leading into the element of digital core analysis and the application of multiscale imaging and digital core analysis for our workflows. Yeah? And of course, again, if you can't understand me somehow or anything is unclear, just let me know. I hope I will be able to see any comments at the same time. It's not so really clear to me what I'm seeing on all the screens here. Yeah. So let's start off. Why do we do core analysis? Why do we take core? And really, what's the application from it? I think the easiest way of looking at that is by just considering a really very small field, like a field which is a mile wide by a mile wide, about 200 feet thick. Let's assume that that little field has a porosity of about 20%, has a 10% water saturation. And if you just take these bulk numbers, you can calculate what we call the stock tank oil originally in place. I hope you can see my mouse or my pointer here, where I'm trying to show you some things. With these dimensions of the field, one calculates that little field, which is about 1/10 of a typical field in the Gulf of Mexico, or maybe 1/10 of a typical field in Brazil, still contains about 150 million barrels of oil. And even at reasonably low oil prices compared to what we're seeing at the moment, the value of such a field, of that stock tank oil initially in place, is about 10 billion. Now, of course, I realize that it's a very simplified calculation. There is a question of recovery at the same time. There is a question of timing, deferred production versus initial production, all those things. But the point that I want to make is that if you take that value, that stock tank oil initially in place, you can calculate what the value is associated with a particular uncertainty in the formation evaluation. So if you are unsure whether your field is 200 feet thick or whether it's 199 or 201 feet, you already creating an uncertainty of about $50 million. 1% uncertainty in the water saturation is twice that value, $116 million. And 1% uncertainty in porosity translates to $500 million of value that needs to be considered. And those differences can make or break a project, right? It can make a project economic, or it can mean that basically the field is too small to be further developed. Now, of course, I mean, you know that we do measurements in the formations, right? We have our well logging tools, but please keep in mind that there is not a single well logging tool that measures the petrophysical properties directly. The properties that we are really interested in are derived from different physical measurements. For instance, a porosity is derived from the measurement of the formation density. A saturation is derived from a formation resistivity. We can use NMR porosities, but really what we are counting there is spins, and we need to translate the spin density into a porosity. So these logging tools need to be calibrated. And the only way of doing that calibration is to directly evaluate the formation properties on core samples that are taken from the formation. I wanted to bring the last point with a bit more specific details here. I said that there is no well logging tool that measures the petrophysical properties directly. We call it porosity tool, but really these are derived values. If you take, for instance, a density tool, and I mentioned that before, I realized, but wanted to make that example a bit more clear. You have a radioactive source, you lower it down into the formation, and you have detectors at different spacing from the source, which measure the scattered X-ray from the minerals and from the pore fluids back into a detector set. That allows you to derive the formation density. Now, in order to translate that formation density into porosity, you need to know the matrix density, the density of the grains themselves, as well as the bulk density of the reservoir fluids. For the density of the formation, the grain density, we have in the industry a measurement which has been established decades ago, where we are using Boyle's law to derive the volume of the grains from the pressure equalization that happens when a reference volume at a higher pressure is equalized into an evacuated sample volume, where the helium in most cases can expand from the reference volume in all the void spaces of the sample chamber into the sample, but not into the grains. And so a simple Boyle's law equation allows you then to calculate the grain volume, and by comparing that to weight, you get the grain density. Very similar to when you look at the saturation measurements. We don't measure saturation, we measure resistivity. Now, no asset manager would be happy if we told that we are seeing maybe 200 ohm meters resistivity here. That is nothing what would tell us for the formation evaluation. We have a tool where we have a transmitter that emits electromagnetic waves for an array induction tool, and you have like an array receiver scattered around the tool where the electromagnetic signal is detected at different distances from the transmitter, and therefore is sensing a wave that goes through different depths of investigation to the formation. Now again, the resistivity itself doesn't tell us much. We need to translate the resistivity to a saturation. We use, in the simplest case, in kind of Archie type behavior, where we believe that the conductivity is entirely produced by the conductivity of the pore fluids, and we can translate the measured conductivity to a saturation in the formation. But in order to do so, we need to know the saturation exponent N and the cementation exponent M. And that is what we are measuring on core samples with, for instance, a resistivity index measurement, where we are slowly desaturating a fully brine saturated sample with a non-conductive oil, ideally the reservoir oil, and are observing how the resistance of that sample increases. And then the slope of that curve, if it's as kind of straight as this one, gives us the saturation exponent that we need to know. Now, what kind of core do we acquire? Well, again, I mean, I know that there's probably a range of experiences in the audience, so let me just quickly summarize the main ways of of taking cores from the reservoirs. The key element is that, or the mostly applied element is that we acquire a full core, typically 4-inch diameter. And the way it works is that you have a coring bit, which is hollow on the inside, basically just like a donut. It is part of a coring borehole assembly, or BHA. It's on the bottom there. And the coring borehole assembly is comprised of basically 2 concentric tubes. One strong outer barrel, as we call it, which conveys the pressure and forces and rotation. And within that outer barrel is an inner barrel that is separated from the outer barrel by 2 bearing assemblies on the top and on the bottom, so that when the outer barrel is rotating, the inner barrel remains stationary. And now you can imagine with that hollow donut bit, if you're drilling to the formation, a cylinder of the formation will remain undisturbed, kind of undisturbed at least, and will rise inside that inner barrel and can then be retrieved to surface. So typically we take about 180 feet of in a single coring run, but that strongly depends on how competent the rock is. The longest run that we have done in Shell in a single core is about 600 feet. Quite long, but also very hard rock. Alternatively to the coring borehole assembly, we can also take samples on, as we call, on wireline. So there are wireline rotary tools where basically a little drill bit can be extruded into the formation, drills into formation, takes a sample and basically collects the sample inside the tool, which is then being pulled back to surface. We have also an option of having a lot of little core barrels shot with explosives into the formation. There, some piece of the formation will be caught in these cylinders and then pulled together with the tool to surface. Of course, we also have cuttings and chips where some of the measurements are done, and especially with the advent of the digital rock technology and the micro CT imaging, these small samples from the formation are becoming more and more interesting in the industry for formation evaluation. You see here on the middle and on the top how the core arrives on the surface when we take it out of the barrel. Again, you see the outer barrel here, the strong one. You see the inner barrel, which is rotationally separated from the outer barrel. A little aluminum liner that makes it easier for the core to rise in the inner barrel. And then inside, that is our first look at what the formation looks like maybe 10 kilometers down the well bore and 200 million years ago. What's very important is that the core remains as undisturbed as possible. So in a lot of regions, not so much in Brazil because of the competent carbonate rock, but in the kind of post-salt reservoirs that you have in Brazil, the BC10 formation, for instance. These are unconsolidated sands, basically beach sand, and it's very difficult to keep that sand together. So what we do on the well site is to freeze that core. So you see like a lot of containers here, where the core is, as soon as it comes out of the well bore, is first put under dry ice, left there for about a day, so that it's hard frozen, and only then you work with that core and you can transport it in a frozen state to the lab where the investigations are conducted. Now, with the huge amount of core that is being taken worldwide, maintaining a database is hugely important. Yeah? And there are services from the industry that can help you with that. And just to point out basically what kind of data volume is being looked at, just for our own internal lab, we currently have about 17,000 cores stored. For each of the core, we have taken hundreds of plugs typically, and on each plug, dozens of individual measurements have been taken. And all these measurements need to be able to be correlated to wells, to well formations, to fields, and compared with different measurements. Yeah? So not a single task can, of course, all be done with the proper databasing, but given that one spends a huge amount of money getting that material to surface, it is very important that the data are properly, the databases are properly maintained. Now, let's switch a little bit to the imaging elements of it. We have just seen that we are able to get core to surface. Now we need to assess what's in the core. And one of the most powerful techniques for doing so is using CT scanning. And as a matter of fact, a lot of the CT scanners that we are using in our industries are CT scanners that have been initially developed for the medical applications. So I'm sure many of you had been being assigned a medical CT scan where you have the table where the patient lies on, and you have a set of detectors, X-ray sources and detectors, which are simultaneously rotating around the sample. Yeah, so this happens in the gantry here, basically around that side, about 1.5 seconds per rotation. And because of that rotation, we get an attenuation of the incident X-ray beam compared to the intensity of the X-ray beam that is being detected on the other side of the sample. And that follows Bayes' law, right? So the basically attenuation is proportional to the combination of bulk density, Compton scattering, photoelectric effects. A variety of the mineralogy plays a role there. And because that attenuation is calculated with a full circumference around the sample, one is able to back calculate the individual attenuation coefficient per voxel. And that helps us to assess the quality of the core. You see, for instance, here in the middle, a core which is actually a Brazilian core, which has been pulled to surface in very good condition. You don't see any fractures. That is a slabbed core, by the way. 1/3 of that core remains with the government. 2/3 can be used for the measurement. And as a contrast to that, on the bottom, also a core from Brazil, you see that damage has been made to the core because the core has been pulled out of the formation too quickly. Basically, what happens is that of course, the pore pressure in the core has, well, a certain pressure, quite a high pressure quite often. And when the core is being pulled out to surface too quickly, and you don't give enough time for that pressure to equalize across the kind of zone of invasion here, what you see with the brighter colors, then the core kind of explodes inside the liner, right? And what you see here with the CT scan, within the resolution of the CT scan, is a very strong fracture. What you don't see is a lot of mini fractures, which are simply below the resolution, but which makes it very difficult to work with such a core. So the core is used for quality control of the measurement. It's used for identifying geological facies. Sorry for my cough here. And we use it then specifically also for looking at on the plug scale to assess the homogeneity of the plug and assess whether a plug would be suitable for special core analysis. So this would be a bad example, by the way. You see quite a heterogeneity in we call it the Hounsfield units. So the attenuation of the X-rays. You see the brighter colors are basically stronger attenuation. You see a bit of invasion on the outside. It is not too much to worry. You could clean it out, but you see wax inside. You see quite a heterogeneous density profile, pseudo-density profile, which means if you would make core flow measurements with that plug, most of the pore flow would go through that channel here on the inside and not all the other elements of that core plug. You would get a biased answer, biased towards the properties of that more permeable section. The medical CT scanners give us a resolution typically on the millimeter scale, maybe 0.7 millimeters or so as a voxel resolution. That is not enough to see the individual pore structures. In order to do that, we are looking at the rock with a higher resolution, and that typically happens with micro CT scanners these days. You see an example here where one of my colleagues is just loading a sample. The sample is tiny now, and we talk about that a bit later. But instead of having an X-ray source and a detector rotating around the sample, we now have a millimeter-sized sample rotating in front of the X-ray source, so that the attenuated X-rays are then being amplified and going into a detector. That allows us to get resolution of maybe a micrometer, and a micrometer is good enough to see individual pore structures. For instance, here you see on a sample the clear difference between the normal pore structure comprised of grains and pores, but also a large fraction of what's called carbonaceous material. So basically fragments, organic fragments have remained in that rock, in that reservoir. And by looking at the pore structure with that resolution, you see that one needs to be very careful how to treat that plug, for instance, in the initial cleaning process. When exposing kind of carbon-like material, core-like material to methanol, for instance, the methanol creates fractures in the carbonaceous material. And these fractures will have a very strong contribution to permeability, potentially even affecting porosity. So that would affect in-place volumes that are calculated and permeability in terms of recoverable volumes. And I don't want to go back to the initial slide, right? But you remember what monetary impact a relatively small variation of saturation and porosity had for even a very small field. We can also look at the rock in a higher resolution. These are beautiful SEM images, which shows us very nice structures of kaolinite and chloride clays surrounding our grain structures. We can also look with SEM at a higher resolution for getting the minerals mapped. So basically with the backscatter electrons, you can get an idea about the individual structures, individual minerals, having the right databases there, and gives you a very clear understanding between quartz and feldspar clay structure, all what's need to know for understanding the pore structure. But let me get back to the micro CT a little bit more, because it's not just that we get pretty pictures from the micro CT. What you see here on the right is just an example of the grayscale image of about 1 micron resolution sandstone. You see in black the pore space, the kind of quartz minerals here in this kind of gray color, feldspars, but also the clay structures here which have a certain microporosity. And with the kind of modern image analysis, you are able to not only segment these pore structures into the individual minerals, but also to compare how the pores are connected to each other. Yeah, that's what's rotating here on the bottom left. Each color represents a cluster of connected pores. And that cluster of connected pores, of course, is related to the resolution of the image. So you need to say that, well, that pore cluster is connected for given the resolution of about 1 micrometer. It might be connected at a lower resolution, but we don't see that. But that's important for the application of digital rock, what I quickly want to introduce here. Yeah, as I said already, we get these beautiful images. Here is an image of a classical micro CT scanner. Means they're called benchtop devices, but to be honest, it weighs about a ton. So you need to have a pretty strong bench to run it. And the one what you have in the LRAP lab, the Corton there is whatever, 5 times that weight, I would say, or 3 times that weight. The workflow that has been developed in the industry, and that is not specific for Shell here, is something called digital rock. It comes in different names for different companies or integrated service providers, but roughly it's always the same. You take a sample, you need to prepare the sample in terms of identifying the heterogeneities roughly, and we are talking about that in a little later. You take mini plugs from these samples, millimeter-sized mini plugs, and you do the high-resolution micro CT imaging. These images, these are 3-dimensional volumes of images, are then processed. Typically, you need filtering. You definitely need some cropping. You can't work with the entire image mostly. You need some segmentation. And then that 3-dimensional structure is used as baseline for simulating the rock properties. It could be as, well, let me call it simple, but as basic as calculating the void space and deriving porosity. It typically also involves making simulations of a pressure wave across the sample to derive permeability, but also electrical and acoustic properties are typically simulated. Keep in mind, the more complex the simulations are, the more assumptions need to be made for these calculations. A porosity calculation is relatively robust within the resolution of the image. And simulation of electrical properties needs to have a handful of assumptions to cover what basically cannot be seen with the micro CT. And then these properties, the rock properties, are upscaled again for the entire core plug and hopefully even to a larger scale to be comparable to the reservoir properties. And what's shown here is the classical porosity-permeability correlation that is used and really populated with individual measurement to derive a trend, which then can be used for the field study, or a plot of relative permeabilities, both drainage and imbibition curves, where the digital rock results are then compared with the actual experimental values. That leads me into spending a bit more time on the multiscale imaging aspects of digital rock. So let's step back for a moment and ask ourselves, what is multiscale imaging and why do we need it? And when preparing the slides, I realized that it's actually much easier to explain when we would not need multiscale imaging. Because if you look at a fractal structure, then we know that fractal structures are typically characterized by a certain self-similarity, or sometimes a bit more wordy, it's called scale invariance of its structures. The classical examples are images of coastlines, where basically the more you zoom in, you get a different image, but the image has the same structure. It's the same functional information that is derived independent of the resolution of the image. Nature has the same for us. In some of the plants, you basically see that the different components of the plants are all built up of the same structures. And then, as you know, right, there are mathematical structures. The Sierpinski triangle or the Menger sponge have very particular structure where the more you zoom in, you get an image which looks very much the same or has the same functional information as the image at a different zoom scale. And because of that, one is able to transfer the structural information across length scales. And in that case, we would not need multiscale imaging. We get the same information from a leaf of a fern compared to looking at a larger piece of that plant. Yeah? Now, in geoscience, we typically don't have that luxury. What we know is that geological structures typically possess heterogeneities at different length scales. And I mean, for the Brazil work with the pre-salt carbonates, I think you are in an almost extreme example of heterogeneity from a geoscience point of view. That is because very complex depositional and diagenetic processes will control the pore structures. And because of that, a single imaging technique, a single resolution, a single physical measurement is not sufficient to adequately describe the entire pore structures. That is shown here with a bit of a cartoon-like description of what measurement techniques, analysis technique, and modeling techniques are used for pores and rocks at different length scales. Yeah, so in nanopores, we typically need tomography, microscopy with very, very high resolution, SEM and TEM, yeah, tomography. The measurement, the physical measurement, is more adsorption, atomic force microscopy, nano infrared spectroscopy. Yeah, modeling, it's typically the small length scale, so molecular dynamics modeling is sufficient. Then we are getting into pores, where we have focused ion beam scanning electron microscopy, making measurement. And the impact here is primarily on the permeability. Then we are getting into larger structure, where we see connection between our individual pores towards fractures, where the geomechanics element become very important. Fracture modeling. Now it could be medical CT or micro CT, probably more micro CT, to see kind of sub-millimeter type fractures. And ultimately, the length scales getting into core, we are working with very different physical measurements, very different uncertainties and challenges for the modeling towards the entire formation, where we're now talking about kilometer length scales. Seismic is kind of the only measurement that we really have there in the subsurface to give the structures. And then the geophysical and basin modeling, where basically the geological information assumption about the geology are made to describe these structures. We have seen that really popping up when we worked a couple of years ago a lot on unconventionals. Again, I don't want to repeat the entire plot here, which shows the same, that different length scales in unconventional reservoirs, so basically the self-sourced shales, require very different measurements. But I just want to point out that because of these very strong structural heterogeneities, the industry actually has made mistakes by believing that one can work with the conventional imaging techniques like medical CT scanning, maybe SEM, to describe the entire pore structure of unconventionals and predict the flow performance in unconventionals. That went very badly. A lot of basically uninterpretable measurements have been made, or wrong modeling results have been obtained. So different length scales have their own physics, have their own structural information, and we need to have the adequate measurement technique and modeling technique to describe these. We are not the only ones who have that situation, right? I was just kind of looking for different length scales and different multiscale imaging application in other industry, and what pops up a lot is the medical industry. And you see here just an example, not that I can really understand it, but just an example taken from a publication where imaging of, I believe that looks like a knee, has been made at different length scales, and basically very different techniques and different information is derived from that one. It's the same for biological research, very interesting stuff. Satellite images with different resolutions are being used to basically track the traces of endangered species and relate that to the structural information of the landscape. You can even see that with sufficient focus, you can kind of see the direction of animals walking and turning towards each other. Yeah? So a very good example of multiscale imaging and the different information that is being derived. Perhaps a bit closer to our applications in porous media is an example of from the battery research groups, where again the structures of the complex electrodes in modern batteries needs to be investigated at different length scales and at different time scales with very different physical methods, in order to describe the entire dynamic behavior that is going on. On the bottom left, you see a cartoon describing the resolution and field of view of various imaging techniques used in the medical industry, also linked to the time requirement for taking an image. So it ranges again from basically nanometer resolutions on 2-photon confocal microscopy to PET scanning, MRI, and so on. And I bring that example primarily here because it introduces two important elements of imaging that I think need to be brought up in such a presentation. That is field of view and resolution. Because basically one can say roughly the higher the image resolution, the lower its field of view. And because we have that generic boundary condition, we do need multiscale imaging. Without it, everything would be fine. We could always take our images at the highest possible resolution and see whatever we need to see. But if we do that, we are always limited with a very small field of view, basically looking at a leaf and trying to predict the properties of an entire forest. The example is shown here again for X-ray scanning, or basically X-ray based imaging techniques, ranging from like the high energy application for airport security, or what you see medical CT imaging, to our micro CT imaging that we already talked, and to X-ray crystallography. So much higher resolution because the wavelengths are much shorter, and correspondingly the photon energy is lower. And we already spoke a little bit about the comparison between medical CT scanning done at a higher energy compared to micro CT scanning done at a lower energy. Here we have, again, I remind that simply a source and detector arrangement rotating around the sample. For the micro CT imaging, we have a sample rotating in front of the detector and an X-ray source. We have differences in the projections and therefore the resolution and of course the image sizes. But the price that we are paying by working with this very high resolution is that we are limited to millimeter sized samples, whereas a medical CT scanner can image an entire core, an entire body. As a matter of fact, somebody could go into the CT scanner and hold the core with their hands to keep it steady. Don't do that, because these core CT scanners have been, their X-ray intensity has been increased by about a factor of 10, so not a good idea to do that. That brings me to the topic of digital skull, because I spoke in the beginning of the presentation about the core analysis techniques. Now at the then afterwards I introduced the imaging aspects. Now digital skull is a technique that combines experimental techniques, traditional core flooding experiments, with the ability to acquire 3D images of the entire rock structure and fluid distributions. So two techniques are mostly used: macro CT imaging or magnetic resonance imaging. You see here an example of a Dynatom device from Tescan, where we have again a small core holder with a small sample and an entire gantry rotating around the sample. You have from the same company the Cortom device in your facility, which allows to scan entire large cores, but the core is rotating in front of detector and source. And if you combine that imaging capability with a core flooding capability, you are able to determine the distribution of clusters of pore fluids inside that rock samples. And that gives a huge advantage for understanding the complex dynamic behavior in these porous structures. What you see here on the bottom right, for instance, are basically pore-scale dynamic experiments carried out in a synchrotron beamline. So from a particle accelerator and the synchrotron X-rays that are beamed off from the circular accelerator, they don't really give us much higher resolution than the benchtop machines, but they are able to make these measurements very, very quickly, within seconds, as opposed to hours or perhaps even days for some of the benchtop machines. And when you do these measurements with very high resolution, you are able to detect how individual individual fluid and gas clusters are connecting and disconnecting. And that leads to a complete new understanding of the multiphase flow in the porous media. Instead of having a homogeneous flow, it is much more like plop, 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 individual gas clusters connecting, disconnecting, and therefore migrating through the porous media. That leads to very important applications. For instance, the determination of a critical gas saturation. Just as a reminder, critical gas saturation, when you deplete the pore pressure of a reservoir and you have a live fluid in it, then when the pore pressure goes below the bubble point, you will release the gas as a single phase. And at some point, the saturation of the gas is so large that the individual gas cluster become connected, and then in that case you will start to produce mainly gas and you leave the oil behind. So huge economic impact on the evaluation to know what is that critical gas saturation. Now it's been experimental techniques for decades, but the problem is experimentally the experiment will affect the result, because in order to measure it you need to impose a pressure gradient across the sample in order to get any flow, to measure what comes out of the sample. But if you have a pressure gradient, you're already creating a gradient in the bubble point, or a gradient of the distance of the pressure to the bubble point of the sample, and therefore, now basically you are affecting the measurement itself. Another application is what's called the trapped gas saturation, and it has a huge impact on carbon capture storage or hydrogen storage. Just imagine the situation. You have a tilted reservoir, you have a injector well, you inject a certain amount of CO2 in that reservoir. The CO2 will slowly migrate upwards in that tilted reservoir. Now, while it's migrating upwards, it's diluting itself because a certain amount of gas remains trapped in the pore structure. Now, you need to know how much is trapped, because at some point somebody will ask you, how far is that plume migrating? How far do I need to be away from another potential leak of CO2 back to surface. And that could be like an old well, or it could be a fault, or could be a fracture where the CO2 would come back to surface. So direct applications of these parameters. And experimentally, very hard to do. Digitally, with multiscale imaging, you can basically make these experiments as shown here on the right. You take a two-phase fluid, you are depleting the pore pressure of the two-phase fluid. And what we are looking here are individual gas clusters only, not the liquid. And different colors indicate different connected gas clusters. And you see at relatively high pressure, you see only very small clusters, a lot of different colors, very disconnected. So basically, we are not in the situation that the gas clusters are connected. But while we are depleting the pore pressure of that rock, you see that eventually a massive red cluster develops connected from the bottom to the top, therefore establishing the critical gas saturation in that case. That has led to workflows for multiscale imaging, and I just, as an example here, a workflow from Ruspini, developed at Imperial College a couple of years ago and published, where, again, one starts imaging, in that case, from the right to the left here, larger scales, whole core or core plugs. The core plugs are identified with their different reservoir rock types. Then individual plugs are taken from these individual reservoir rocks, imaged at a higher resolution. Resolved and unresolved porosity is being evaluated. You see that different techniques are being used, between basically medical CT scanning to micro CT scanning to focused ion beam SEM scanning. And then once all the ingredients have been characterized for their reservoir properties, the rock is populated back with the properties of the individual components and the volume fractions of these components, and the results are upscaled to give an effective property of the entire rock. So quite an elegant workflow, and one way or another, that is a workflow that has been established in the industry in kind of some form from a variety of sources. An example of that, and I'm slowly coming to an end here, is a very neat experiment that has been published by Sam Crever, also from ICL, in the SCA conference last year, where he demonstrated how the experiments for basically gas brine drainage co-flooding experiments are being used in combination with the imaging of the pore structure. So you see here just a little PNID diagram of the gas flooding unit. The key here is a core holder inside a micro CT scanner. The micro CT scanner is used in combination with what's called wet and dry scanning to basically the core is scanned twice, once without fluid in it, second time with fluid in it. And from the difference images, one can determine the fluid saturation at each voxel. In parallel to that, the rock is also scanned for its porosity distribution. Here are the 3 different samples where that has been done. And then by combining the information at each voxel and assuming a certain capillary pressure behavior, one can determine the capillary pressure, the entry pressure in each of these voxels that are measured. And that is exactly the information that is needed to predict, for instance, the CO2 flooding through the porous structure. Because if the pressure at which the capillary pressure between the CO2 brine system, if that exceeds the entry pressure into a certain pore, then one can assume that the CO2 will enter that pore. It's kind of a logical thing there. But that is a very neat indication, in my opinion, where the scanning at different length scales results into a workflow for digitally describing the pore scale dynamic processes. Maybe closer to an application, and that is my final example here, is an indication of multiscale imaging for the identification of salt-bearing sediments. That we have done that in the Gulf of Mexico. There are some formations where the brine is immensely saline, 400,000 ppm at a reservoir condition. You can't even recreate that brine in the lab. And so the rock, in many cases, it shows really almost like shiny, like silvery, because of the salt. When you take a medical CT image, it looks like that, right? So you see highly bedded, thinly bedded formations, but strong differences in the CT appearances. Taking plugs at the indicated locations here of the core shows you already on the medical CT scanner very different kind of structure information. Laminations, much more of a homogeneous rock, a much tighter rock here. If we then take mini plugs at each of these macro plugs, we see a strongly contrasting behavior from an area where the pore space is completely saturated with salt to an area where the pore space is almost free of salt. And that helps then to create a correlation between the attenuation coefficients from the medical CT imaging and the porosity information that is derived from the high resolution mini plugs that have been scanned on the micro CT scanner. And with that correlation in mind, one can get an information of porosity directly from the medical CT scan, well, and then upscale that to the log and compare to a variety of other logs, like 2 different NMR acquisitions here. And the correlation is not bad. It's not perfect. It's a correlation. It's not a direct causation, right? But you see that most of the trends of that reservoir properties have been properly summarized. So this is what I wanted to show you. I hope I have shown you that multiscale imaging and multiscale analysis workflows are typically required to address the heterogeneities that are dependent on the length scales in complex materials. Yeah? We have discussed that a single resolution, images with a single resolution, can not capture the different physical and chemical processes, but that scale-dependent heterogeneities need to be accounted for in these multiscale workflows. Yeah? And with this, I would like to finish here and are open if you have any questions. I can't hear you, by the way, but no. Perfect.
Can you hear now?
Yes, I can hear you now.
Okay, the microphone is off here. So time for some questions now. Let me just turn on the lights. So thank you, Mathias, for a brilliant presentation. Thank you so much.
Sure.
Do you have time for some questions? Do you have any? Temos alguma pergunta na?
Não,
online?
não.
We just had another presentation just before you. Dr. Rodrigo Silva from Sempis was also talking about digital rock physics using several images from several scales.
Mm-hmm.
And we were talking about speeding up this measurements using artificial intelligence techniques.
Mm-hmm.
How do you see the use of artificial intelligence techniques?
Yeah.
With images in several scales, as you mentioned.
Yeah, it's a very valid question, a very valid point. So the image processing scale workflows is indeed very time consuming. It's absolutely right. So there are different approaches for network models which are faster but have limitations than direct simulation of different scales, which are quite often limited in terms of what length scales can be simulated, and that is where the AI elements come in. I think it can be hugely powerful as long as one takes the time to properly train these AI networks and spends the time to identify what are indeed the proper basically training data sets from which the AI protocols can populate the unknown parameters. This is sometimes a challenge, I would say, because of the intrinsic heterogeneity that we see of the rock. I think it's also a particular challenge for, say, the pre-salt carbonates there. Of course, one could keep the training set very generic and say, well, that's a piece of rocks, and of course it will find also other pieces of rock like that. But in order to make it quantitative, I would say that the focus really need to be on identifying a representative data set on which the AI workflow can be educated before it's being applied.
Thank you. Thank you very much. We do have time for more questions. Oh, any questions? Something like share? Okay. Any question from the audience?
No. No.
Okay. So Mathias, thank you once more for your brilliant presentation. And we'll be back here at 2 o'clock Brazilian time. This is from about 70 minutes from now for the presentation of Professor Behzad Gambarian from Kansas State University. Thank you very much, Mathias. So if you want to join us later, you're our guest.
Thank you very much.
So much.
Bye-bye.
See you later.